Sequences and series. A sequence is a function whose domain is the set of positive integers. The function values are called the terms of the sequence. So, for example, here is a linear function, f of x equals 5x minus 2. If we restrict the domain of this function to only be the positive integers 1, 2, 3, 4, 5, and so on, then we will have what we call a sequence. So for instance now, the first term would be what I get when I plug 1 into this function. 5 times 1 would be 5, minus 2 would equal 3. So I have that the f of 1 is equal to 3. If I plug 2 in, which is the next positive integer, well, 5 times 2 is 10, 10 minus 2 is 8. So the second term in the sequence would be the f of 2, 8. The third term would be 5 times 3, which is 15 minus 2, which is 13. So the f of 3 would be 13. And then if I plug 4 in, 5 times 4 is 20, and 20 minus 2 is 18. So the fourth term in the sequence would be 18. And you could continue doing this as long as you want, because there is no largest positive integer, so you could continue this forever, meaning this sequence is an infinite string of numbers, an infinite sequence of numbers that would continue on forever. So the terms of the sequence would just be 3, 8, 13, 18, and you would just keep going. The next one would be, of course, 23, and then 28, and you could keep going with this sequence. Let's talk about the notation of sequences. So sequence notation. The variable a with a number subscript is used to represent the terms in a sequence and to indicate the position of the term in the sequence. So for instance, the first term of the sequence would be an a with a subscript of 1 as its representation. So the second term would just be a with a subscript of 2. That shows that this term is the second term in the sequence, so the position is 2. The third term would be a with a subscript of 3. The fourth term would be a with a subscript of 4. You could continue on with this, and let's say we want to describe not a specific term, but just the general term of the sequence. Well, we call that the nth term of the sequence. And the nth term, or the general term of the sequence, is an a with a subscript of n. You can get an explicit formula for that nth term by simply looking at the function that generates the terms. You'll notice that this generating function is nothing more than the original function that we had, that linear function 5x minus 2, with the x replaced by the letter n. So f of x kind of implies we're talking about x being any real number, while an means that we are only looking at positive integers as the inputs. So that is the notation of sequences. Let's look at an example. Let's write a formula for the nth term of this sequence here. The sequence has the first term 9, the second term 16, third term 23, the fourth term is 30, and the fifth term is 37. And we can use the notation to symbolize that. So we have A1 is 9, A2 is 16, A3 is 23, A4 is 30, and A5 is 37. You'll notice that the difference between consecutive terms here is always the same number. So for instance, A2 minus A1 is just 16 minus 9, which is 7. A3 minus A2, which is 23 minus 16, that's also 7. A4 minus A3, which is 30 minus 23, that's also 7. A5 minus A4 is 37 minus 30, which is also 7. When each of the terms of a sequence, each consecutive term, differs by the exact same amount, we have a special kind of sequence. An arithmetic sequence is a sequence in which each term after the first term differs from the preceding term by a constant amount, that constant amount here being 7. The difference between consecutive terms is called the common difference of the sequence, And an explicit formula for the nth term of an arithmetic sequence is given by the formula an, which is the general term, is equal to a1, the first term, plus that common difference d multiplied by n minus 1. So we have that the common difference of this sequence is 7, and that the first term of the sequence a1 is 9. So just plugging those numbers into this formula, we get an is equal to 9, which is the first term, plus 7, which is the common difference, times n minus 1. This is a formula for the general or nth term of the sequence. We can simplify this by distributing, so 7 times n, and then 7 times negative 1 would give me 7n minus 7 here, and that 9 is still there. And then you combine the like terms, the 9 minus the 7 would give me an equals 7n plus 2. You'll notice that this is a linear expression, mx plus b. That's a feature of all arithmetic sequences. If the function that the sequence's terms are generated by is a linear function, you will always have an arithmetic sequence, and the slope of that arithmetic sequence will be the common difference. Let's take a look at another example here. Write a formula for the nth term of the sequence. And we have here the sequence 2, 6, 18, 54, 162, and it continues like that. You'll notice that this one is not arithmetic because the difference between consecutive terms is not always the same number. For instance, the difference between 6 and 2 is 4, while the difference between 18 and 6 is 12. So this is not an arithmetic sequence. Let's look at each individual term, a1, a2, a3, a4, a5, and see if we can't find a relationship. We have that the quotient of a2 to a1, a2 divided by a1, 6 over 2 is equal to 3. And the quotient of the next two consecutive terms, a3 and a2, which is 18 divided by 6, is also 3. And the quotient of the next two consecutive terms, a4 and a3, 54 divided by 18, is also 3. And the quotient of the last two terms that are presented here, a5 and a4, that quotient is also equal to 3. So in this case, instead of having a common difference between consecutive terms, we have what's called a common ratio of 3. Well, whenever consecutive terms have the same common ratio, we get the type of sequence that's called a geometric sequence. A geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed non-zero constant, in this case 3. The amount by which we multiply each time is called the common ratio of the sequence, and an explicit formula for the nth term of a geometric sequence is given by an is equal to a1, the first term, multiplied by the common ratio raised to the power of n minus 1. So since we know the first term 2 here, and we know the common ratio 3 here, we can actually get an explicit formula for the general term or the nth term of the sequence. It's just going to equal an equals 2, which is the first term, multiplied by 3, which is the common ratio raised to the power of n minus 1. Those are two special kinds of sequences that we will be studying, arithmetic sequences and geometric sequences. All right, let's take a look at another example here. It says, write the first 5 terms of the sequence. And we have here a sequence, an is equal to 3 to the power of n minus 2. Now this one is not really arithmetic or geometric. Because of that minus 2, it's not necessarily geometric, but this is just another function that we've used to create a sequence. So to find the terms of the sequence, we simply plug in the positive integers. So the first positive integer we'll plug in is 1. So a1 is 3 to the first power, which is 3, minus 2, which is just 1. That's the first term. The second term, a2, is 3 to the second power. 3 to the second power is 9, and 9 minus 2 is 7. The third term, a3, is 3 to the third power, which is 27. 27 minus 2 is equal to 25. The fourth term, that's 3 to the fourth power, which is 81, and then 81 minus 2 will give us 79. And then the fifth term, that's 3 to the fifth power, which is 243, and then 243 minus 2 is equal to 241. The terms of this sequence are, the first 5 terms are 1, 7, 25, 79, 241. And that is how we would list the terms of a sequence given the general or nth term of the sequence. So let's define a recursive formula. So we saw the explicit formula. Now let's define what a recursive formula is. A recursive formula is a formula that defines each term of a sequence using preceding terms. So rather than using the position of the term, we're using preceding terms instead. Recursive formulas must always state the initial term or terms of the sequence. So here is a recursive formula. We have the first 2 terms given, a1 is 1, a2 is also 1, but the recursive formula says that an is equal to an minus 1, which is the term that comes before an, plus an minus 2, which is the term 2 terms before an. To find a3, for example, a3 would just be a2, which is the term before, plus a1, which is the term before that. So we're just adding 1 plus 1 to get 2. That's the third term. To get the fourth term, we have to add the third term and the second term. So the term before the fourth and the term 2 terms before the fourth, the third and second terms. So a4 is 2 plus 1, which is 3. a5 would just add a4 and a3. So a5 is 3 plus 2, which is 5. And a6 would just be the sum of a5 and a4. So a6 is equal to 8. a7 would just be the sum of a6 and a5. So a7 would equal 8 plus 5, which is 13. And this is how we use a recursive formula. When you're using a recursive formula, you're going to have to refer to previous terms in order to get the current term. All right, so that's how recursive formulas work. And this specific sequence with this recursive definition is called the Fibonacci sequence. Okay, let's look at another example here. Here we have another recursive definition. So in this case, the general term isn't based on just the position, or n, but based on the term that came before it, an minus 1. So this says that an is equal to 3 times an minus 1, the previous term, plus 5. Since a1 is equal to 4, that an minus 1 in the formula is referring to the 4, the term that came before it, when I'm trying to find a2. So a2 would be 3 times 4, which is 12, and then 12 plus 5 is the 17 that I get for a2. And then to find a3, I'm referring to a2 now. So it's going to be 3 times the one that came before for a3, which is a2, plus 5. 3 times 17 plus 5 is equal to 56. 3 times 17 being 51, and then 51 plus 5 is 56. To get the fourth term, I'm going to do 3 times 56 plus 5, and 3 times 56 plus 5 is 173. And then to get the fifth term, I'm going to do 3 times 173 plus 5. 3 times 173 plus 5 is 524. And you can continue in this fashion to find subsequent terms. And that's how recursive definitions work. Let's define factorials. So, given the positive integer n, the notation n with an exclamation point is read n factorial and is the product of all positive integers from n down to 1. So for instance, n factorial then can be defined as n times n minus 1, which is the integer before it, times n minus 2, which is the integer before that, and you go all the way down 3 times 2 times 1. You go all the way down to 1. By definition, 0 factorial is equal to 1. So that's just a definition. 0 factorial is equal to 1. All right, let's look at an example here. 5 factorial. Well, 5 factorial would just be 5 times 4 times 3 times 2 times 1. So all the positive integers from n all the way down to 1. 5 times 4 times 3 times 2 times 1 is equal to 120. So 5 factorial is 120. You're taking the number in front of the exclamation point or the factorial symbol, and you're multiplying it by all the positive integers from that number all the way down to 1. So here's an example. Write the first 4 terms of the sequence with this general term. So this is the nth term of the sequence. We're just going to plug in n from 1 all the way up to 4 because we are finding the first 4 terms. First we'll plug in 1 to find the first term. So a1 is 3 to the first power divided by 1 factorial. But 1 factorial is just 1 because it's the product of 1 and all the positive integers down to 1, so that's just 1. So 3 divided by 1 is 3. Now we look at a2 would be 3 to the second power, because now n is 2, divided by 2 factorial. Well, 3 to the second power is 9, but 2 factorial is just 2 times 1, which is 2. All right, now the third term in the sequence, a3, well, on top we'd have 3 to the third power, which is 27. On the bottom we'd have 3 factorial, which is 3 times 2 times 1. 3 times 2 is 6. 6 times 1 is also 6. So we get 27 over 6, which we can reduce to 9 over 2. The next one, a4, the last one we're looking for, well, that's just going to be 3 to the fourth power over 4 factorial. Well, 3 to the fourth power is 81, but 4 factorial is 4 times 3, which is 12, times 2, which is 24 times 1. So 4 times 3 times 2 times 1 would give me 24. And then we can reduce 81 over 24 because 3 goes into both. 27 over 8 is the reduced fraction. This sequence, the first 4 terms of the sequence are 3, 9 halves, 9 halves, and 27 eighths. But you could continue on with this to find more terms. So this is how we would evaluate a sequence that contains a factorial. All right, now let's look at defining partial sums. Partial sums. So the sum of the terms of a sequence is called a series. So whenever we add up the terms of a sequence, we get what we call a series. The nth partial sum is the sum of a finite number of consecutive terms beginning with the first term. So the notation Sn represents the nth partial sum. So let's take a look at this sequence as an example. For this sequence, the symbol S1 would represent the sum of its first term. So S1 is just 1, basically just the first term. On the other hand, S2 would represent the sum of the first 2 terms. So that would be S2 equals 1 plus 7, adding the first 2 terms up, which is 8. So that would be the second partial sum. The third partial sum, S3, would be 1 plus 7, which we already know is 8, plus 25, the next term in the sequence. So 8 plus 25 is 33. So the third partial sum for this given sequence here would be 33. The fourth partial sum is 1 plus 7 plus 25 plus 79. We already know that 1 plus 7 plus 25 is 33. When we add 79 to that, we get 112. That's the fourth partial sum for this series. The fifth partial sum for this series would be 1 plus 7 plus 25 plus 79 plus 241, basically adding up the first 5 terms of the series and we get 353 for that answer. So the nth partial sum, or the fifth partial sum here, would be 353, adding up the first 5 terms in this sequence. So that's how we find partial sums, and you could continue in this fashion. So this sequence of partial sums actually creates its own sequence. So now we'll talk about summation notation. Summation notation. Summation or sigma notation is used to represent series. So summation notation is used to represent the sum of the terms of a sequence. Summation notation includes an explicit formula and specifies the first and last terms in the series. An explicit formula for each term of the series is given to the right of the sigma, which is a Greek letter, it's a capital sigma. A variable called the index of the summation is written below the sigma. The index of the summation is set equal to the lower limit of the summation, which is the number used to generate the first term in the series. The number above the sigma, called the upper limit of the summation, is the number used to generate the last term in the series. So let's take a look at this notation. Here is a summation notation here. We have the index of the summation is this variable I, and you notice that the explicit formula will have I as this variable. The lower limit of the summation is the number used to generate the first term in the series. The upper limit of the summation is the number used to generate the last term of the series. And of course here we have the explicit formula for the ith term of the sequence. All right, let's look at an example and see if we can't make sense of this. Here's an example. It wants me to evaluate this sigma notation here. So I have the index of the summation being I, and you'll notice that the explicit formula is for the ith term. They want me to start with the lower limit to generate the first term, which is when I is equal to 1, and the upper limit is the last term I'm going to evaluate, where I is equal to 4. So the summation then would look like this. I'd have, this would be the first term that I'm adding, 3 times 1 plus 5, which is 8. So 8 is the first term in my series. The second term I'm adding is 3 times 2 plus 5. That's the second term in the sequence. So I'm adding that. 3 times 2 is 6. 6 plus 5 is 11. So I'm adding 11 next. Then the third term in the series, well, that's 3 times 3, which is 9. 9 plus 5 gives me 14. So the third thing I'm adding is a 14. And since the upper limit is 4, that's the last term I'm going to generate here. So the fourth term is 3 times 4, which is 12. 12 plus 5 is 17. So this sum is what this summation notation is representing. We start with the lower limit 1, and we generate the term 1, and we go all the way up to the upper limit 4, and we generate the term of 4. We generate all the sequence terms in the middle, and we just add them all up. This sum is going to be 50. 8 plus 11 plus 14 plus 17 is just 50. So that's how you evaluate summation notation. Let's look at one last example. So here we have the summation notation. The index of the summation is still I, so I is the variable we use in the explicit formula for the terms of the sequence. But in this case, the lower limit is 3, so I'm going to start with the first term being actually the third term. The first term in the series would actually be the third term of the sequence. And I'm going to go all the way up to the fifth term of the sequence, and I'm just going to add all those up. So here we go. So first I'm starting with the third term. So A3 is 2 to the third power. 2 to the third power is 8. Then I'm moving on to the fourth term. Well, that's 2 to the fourth power. 2 to the fourth power is 16. That's the fourth term. And the last term, based on this upper limit, the last term is 2 to the fifth power. That's the fifth term. and 2 to the 5th power is 32. If I were to add these all up, 32 plus 16 plus 8, I would get the sum, which is 56. So this summation is equal to 56.